You see, if you take a bit of it, it looks a bit like a quadratic. But a quadratic, of course, would go, and it would go off like this. But another part of it, if you said, oh, well, instead of a quadratic, what about a cubic? And all of a sudden, it matches it a little bit better. But it turns back, a sine function turns back up, and a cubic finishes like this and this. So you think, I'll make it a quartic, and then I'll have another turn. I make it a power of 5, and I'll have another turn. And what happens is, if you do that enough times, you get a function that's very close. So when I say cubic, I mean like x cubed plus x squared plus x, something like that is a cubic function that looks a bit like that. But it's not going to match the sine function all the way along, is it? But you could get one matching it pretty close around 0. Like if you just started to do it, you could make a cubic match it. Eventually, like if you're on Desmos or GeoGebra or something, you can get one pretty close. And if you had x to the power 5, that would put an extra couple of turns in, and that would match it even further away, yeah? And then x to the power 7, it would start to match it further away. So what a Maclaurin series or Taylor series does is it tries to match a polynomial to a non-polynomial function. And a Maclaurin series is a particular case of a Taylor series where you match it starting at 0. You start from here and try to match it. So you go, right, if I just have this bit, well, that would just be a linear. But if I put a cubic in, that would match this much up to here. And if I put a x to the power 4 in, x to the power 5. So you see in your formula booklet, they're series. They add up. They go like 1 plus x squared plus x to the power 4 plus x to the power 6 and so on. So that's as we get further away from the initial point, it's matching it. So if you want to match it down way down the line, you have to have loads of powers of x up to x to the power 20 or something like that would match it like after 10 turns or whatever. So that's what Maclaurin and Taylor series does. And it uses the derivatives to match the slope. At any particular point, as close to 0, they start to match the derivatives, because if the derivative of the original matches the derivative of the polynomial, then it'll match the shape of the function. So well, polynomials are far more easy to derive and integrate than some like an ln x sine x function. If you start to go, let's derive that, let's integrate that, that's a mess. But if you have a polynomial, you can do it in 2 seconds. You can derive this, as long as the polynomial matches in the area you're looking at. So for Maclaurin, we're looking at around 0. It won't really match outside like a 200 or something. It won't match there, but around 0. Taylor series is where you match it anywhere along, and I'll show you the difference between the two in a second. We only have Maclaurin series on our but if you want to do an IA or something, you can bring the Taylor series in, maybe if you fancy that. So this is what it looks like, the formula. Yeah, you probably don't. But so this is what the Taylor series looks like. This is where you match it anywhere along the line. So A could be anywhere. It could be like a 10 or whatever. We try and match the function around 10 on the x-axis. But Maclaurin series matches the function starting at 0 on the x-axis. And we build up the polynomial. You see it?
Pretty much the same thing. You just multiply by x minus a.
Yeah, you're building up a polynomial that matches using derivatives. So using the slope. So if the slope of the polynomial matches the slope of the actual function as we go along the line, you're going to match the function to each other. And the more of these derivatives you do, the further away you get from.
But you'll get to like 0, to a constant, and then you'll get 0
No.
for the function on the top now.
No, this is derivative with, yeah. So these are not polynomial functions you're going to derive. These are sine, cosine, ln. Yeah, they're going to keep going. So you notice e to the x repeats all the time, forever. Sine x will go to cosine x, will go to sine x, cosine x. The sign will change, but you see. Yeah, you won't be doing much integrating in this one. Yeah, no DI. But yeah, you see what's happening. These are only for non-polynomial. You're trying to turn them into a polynomial for a section of it close to 0, and that's the Maclaurin series. Okay, so let's look at what we need to do. So what we'll do is we'll just look at cosine x. We're going to use the formula. So this formula is from your formula booklet, because I didn't take. You have this in your formula book. This Maclaurin series that f of x, we match the function at 0, and then we go, right, we match the first derivative at 0, and then we're creating this function as we polynomial as we go along. What does it look like with the x squared part of it? We look at the second derivative for that, for the second term, let's say. And this is given to us. So we're going to try and see f triple dash 0 x cubed. So this is in your formula booklet. You might have found it already, something like that. Okay, so we're just going to look at cosine x because you've just done it. Yeah. They give you, yeah, it's in your formula booklet. All right. So let's say f of x is cosine x. We're going to use the Maclaurin series to turn this cosine function, which we know what it looks like anyway, into a polynomial that looks similar. That's what we're going to do. All right. So let's just do it. If you want to do it faster than me, you can. F with 0 put in. This is why we did this starter. Cosine 0 is 1. Okay? So that means the first, you're going to have a 1 here. 1. Right. Let's do first derivative of x. You've just done it. So first derivative of cosine x is? Negative, thank you. Negative sine x. I don't need to put it in brackets. What's the f dash 0 then?
0.
All right, f double dash then? in order to get to the end point. What's negative cosine 0? Negative 1. Okay, let's do a few more. The third derivative then is going to be back to sine x, and f triple dash 0 is equal to sine 0, which is 0. Let's do the fourth. Derivative again.
Cosine x.
Thank you. F fourth, what's
1.0.
Cosine of 0 is back to 1. Okay. All right, how did this help us form a polynomial? Well, there's going to be some... Yeah, just plug in the values, and it's going to make the polynomial for us, this thing. So the polynomial, you're going to see they're going to miss some terms in this polynomial. There mightn't be a x term. There mightn't be an x cubed term. But there's x squareds, x to the 4s, I think, going to happen. I think. So f at 0 is 1. We did that. F dash 0 is 0, so there's no x term. F double dash 0 is minus 1, so the next term is minus x squared, minus 1x squared over 2 factorial is just over 2, yeah? There's no x cubed, so the next one is going to be x4, isn't it? x4 over 4 factorial
24. No, 24.
Over 24. Well, you probably could see the pattern. What's the next one going to be?
X to the 6.
Plus or minus?
Minus.
Minus x to the 6. And what's the factorial going to be?
6 factorial.
6 factorial, which is?
Times 5 is 30.
720 maybe?
360.
720.
720. Okay. All right. Let's have a look at Desmos. Let's have a look at Desmos. Okay. Desmos.
120 times 30. That's 30. What? You said 120 times 30. Wait, no, 120, that's 360. Yep, 360 times 2.
Okay, that's what cos x looks like. Not too bad. Let's do our new function.
Not too bad.
Well, we knew what that is. 1, okay. Minus, you guys probably faster, x squared.
Wait, you get insert bracket. Oh,
What? 5/2. Okay, see the way it's matching it for close to 0, but not very far away from that. So let's put in the extra one that we created, plus, what was it, x4. Oh, see, we're matching it a bit more. We're matching it further down the line, which is pretty. And then we're going to take away the next one, x to 6. Oh, so slow.
Oh.
Sorry.
Wait, what is the 6 at the bottom mean? In math, does that mean anything? Chemistry, that's like.
Oh, it's 270, is it? Or 720?
720.
720. Okay, it's matching it up to this point, about up to here.
Far. You have to do so many terms for it to be useful.
Yeah, that's why it's most accurate close to 0, and the further away you need more and more derivations. But you can get more. You can do it all the way down the line. That's why the Taylor one is probably slightly better, as in you can